Why the multiverse could be real. As a researcher deeply immersed in the mysteries of the universe, I have always been fascinated by the idea that ours might not be the only reality. What once seemed like mere science fiction has gradually evolved into a serious scientific consideration, backed by rigorous theoretical frameworks and mounting indirect evidence. The concept of the multiverse, multiple universes existing beyond our own, is no longer confined to the realms of speculative thought. It is now a hypothesis with substantial scientific merit. In this exploration, I will delve into the theoretical foundations, observational clues, and philosophical implications that suggest the multiverse could very well be a fundamental feature of reality itself. The quantum foundation, many worlds interpretation. One of the most compelling arguments for the existence of a multiverse comes from the realm of quantum mechanics, particularly through the many worlds interpretation, MWI, proposed by physicist Hugh Everett III in 1957. At its core, the MWI challenges the traditional understanding of quantum measurement, which posits that quantum superpositions collapse into a single outcome upon observation. Instead, Everett suggested that every quantum event branches reality into multiple coexisting universes, each representing a different outcome of the event. This interpretation offers an elegant resolution to some of the most perplexing problems in quantum mechanics, including the infamous Schrödinger's cat paradox. Rather than the cat being simultaneously alive and dead until observed, the MWI suggests that both outcomes occur in separate branching universes. This deterministic evolution of the universal wave function, governed by the Schrödinger equation, eliminates the need for an arbitrary collapse of the wave function. What excites me about the MWI is its methodological minimalism. Unlike other interpretations of quantum mechanics which introduce additional assumptions or mechanisms, the MWI flows naturally from the mathematics of quantum theory. As physicist Sean Carroll has noted, the branching of universes is an inevitable outcome of the formalism when taken at face value. This means that the multiverse is not an arbitrary addition to quantum mechanics, but a consequence of its foundational principles. Cosmic inflation and eternal inflation. Another avenue pointing toward the multiverse comes from cosmic inflation, a theory that has profoundly shaped our understanding of the early universe. Developed by pioneers like Alan Guth, Andre Linde, and others, inflation proposes that the universe underwent a period of exponential expansion in its earliest moments, far outpacing the speed of light. The critical insight here is that inflation, once initiated, may never truly cease in its entirety. While inflation ends in some regions of the cosmos, giving rise to universes like ours, it may continue indefinitely in other regions, leading to an ever-expanding network of bubble universes. This scenario, known as eternal inflation, suggests a fractal multiverse composed of an infinite collection of universe bubbles, each potentially possessing different physical laws and constants. The appeal of eternal inflation lies in its natural emergence from well-established cosmological principles. Most models of inflation, including the widely accepted scenario of eternal inflation, inherently lead to the formation of multiple universes. Furthermore, cosmic inflation itself is strongly supported by observational evidence, such as the uniformity of the cosmic microwave background, CMB, as measured by satellites like WMAP and Planck. The fine-tuning problem. One of the most intriguing aspects of the multiverse hypothesis is its ability to address the fine-tuning problem, a puzzle that has puzzled physicists for decades. The fundamental constants of nature, such as the strength of gravity, the mass of electrons, and the cosmological constant, appear astonishingly fine-tuned to allow for the existence of life. Even slight deviations in these constants would render the universe inhospitable to stars, galaxies, and ultimately, life itself. For example, the cosmological constant, which governs the rate of the universe's expansion, is fine-tuned to an extraordinary degree, estimated to be accurate to 1 part in 10 circumflex 120. Such precision seems almost miraculous, raising the question of whether this fine-tuning is a result of design or sheer chance. The multiverse offers a compelling solution. If there are innumerable universes with randomly varying physical constants, it becomes statistically inevitable that some will possess the necessary conditions for life. Our existence in a life-permitting universe is not the result of intentional design, but merely a consequence of our inability to observe universes where life does not exist. This explanation, known as the anthropic principle, provides a naturalistic account of fine-tuning without invoking supernatural intervention. String theory and extra dimensions. String theory, while still in its theoretical infancy, offers yet another pathway to the multiverse. This framework aims to reconcile quantum mechanics with general relativity by positing that the fundamental building blocks of the universe are not point-like particles, but one-dimensional strings that vibrate at different frequencies. A defining feature of string theory is the requirement for additional spatial dimensions, either 10 in superstring theory or 11 in M theory. These extra dimensions must be compactified or curled up at scales far smaller than the observable universe to remain hidden from direct observation. However, different configurations of these compactified dimensions can produce universes with distinct physical laws and particle properties. This phenomenon gives rise to the string landscape, a vast collection of possible universe configurations, each corresponding to different ways of arranging the extra dimensions. The string landscape is often envisioned as a multi-dimensional terrain, where each valley represents a different universe with its own set of physical constants. Our universe is just one of countless valleys scattered across this vast landscape, each inhabited by its own set of fundamental laws. Observational evidence and future prospects. While other universes, by definition, lie beyond our direct observational reach, scientists have nevertheless sought indirect evidence for their existence. One promising avenue is the study of the cosmic microwave background, CMB, the afterglow of the Big Bang. Researchers have searched for telltale signs of interactions between our universe and others, such as collisions between universe bubbles in the distant past. A notable study led by cosmologist Hiranya Paris identified data consistent with features that could arise from such collisions. While this evidence is preliminary and requires further confirmation, it represents an exciting step toward potentially observing signatures of a multiverse. Additionally, unusual features in the CMB, such as the enigmatic cold spot, have been interpreted by some as potential multiverse indicators. Mathematical universes. Perhaps the most radical multiverse hypothesis is the mathematical universe hypothesis, MUH, proposed by cosmologist Max Tegmark. This idea posits that our external physical reality is itself a mathematical structure, and that all possible mathematical structures exist physically. In this view, the multiverse encompasses not just universes with different physical constants, but universes governed by entirely different mathematical principles. The MUH addresses a long-standing philosophical question. Why is mathematics so unreasonably effective in describing the physical world? If physical reality is fundamentally mathematical, then the effectiveness of mathematics is not surprising. It is the language in which reality is written. Current scientific status and future directions. The multiverse remains a hypothesis rather than an established theory, and it faces legitimate critiques. Some argue that it is unfalsifiable, making it difficult to test experimentally and thereby beyond the purview of science. Others question whether the multiverse truly explains fine-tuning or merely shifts the problem to a higher level. Despite these challenges, the multiverse concept has gained credibility because it emerges from well-established theories rather than being invented ad hoc to solve specific problems. As theoretical physicist Alexander Vilenkin has noted, confirming features in the CMB consistent with universe collisions would be a tremendously important development in our understanding of reality. Recent advancements in quantum mechanics, cosmology, and string theory continue to strengthen the theoretical case for the multiverse. While direct proof may remain elusive, the convergence of multiple lines of evidence suggests that the multiverse is a hypothesis worth taking seriously. In conclusion, the multiverse is not merely a whimsical fantasy, It represents the logical extension of our most profound scientific theories. Whether through the branching realities of quantum mechanics, the eternal inflation of the cosmos, the string landscape, or the mathematical fabric of existence. The idea that we are part of a vast multiverse is a testament to the boundless possibilities of the universe, and perhaps the universes beyond our own.